On July the 1st, 2025, a telescope quietly sitting in the mountains of Chile caught a single point of light moving across the sky in a way that nothing in our solar system moves. It wasn't orbiting the sun, it was passing through. And in the months that followed, some of the smartest people on the planet, NASA scientists, Harvard astrophysicists, teams at the European Space Agency, would spend sleepless nights arguing about what exactly they were looking at. Was it just a comet? A frozen, tumbling relic that had been drifting through the galaxy for billions of years before it happened to wander into our neighborhood? Or was it something else? Something that shouldn't exist? Something that, depending on who you ask, might not be natural at all? This is the story of 3I Atlas, the third confirmed interstellar object ever detected in our solar system, and the strange, unresolved argument about whether it's the most ancient comet humanity has ever studied, or something far stranger wearing a comet's disguise. Let's start with what we know for certain, because the facts alone are wild enough before you even get to the speculation. The object was first spotted by the ATLAS survey, that's the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built specifically to scan the skies for anything that might be a threat to Earth. The station in Rio Hurtado, Chile, picked it up as a faint moving speck. At the time it was discovered, it was roughly 410 million miles from the Sun, sitting inside the orbit of Jupiter, and it was moving at about 137,000 miles per hour. For context, that is fast. Objects that belong to our solar system, things like asteroids and short-period comets, move in predictable, closed loops around the Sun, bound by gravity, recycling the same path over and over for millions of years. This thing wasn't doing that. When astronomers plotted its trajectory, they found something called a hyperbolic orbit, a path so extreme, so open, that the Sun's gravity could never capture it into a loop. It doesn't matter how many times it swings past us. It is never coming back. It arrived from outside the solar system, and it is leaving the solar system permanently, forever. That single fact, a hyperbolic trajectory with an eccentricity measured at over 6, when anything above 1 is technically considered unbound, is what confirmed this object came from interstellar space. Not from the asteroid belt, not from the Oort cloud, from somewhere out among the stars, flung loose eons ago by some other star system entirely, and now, for a few brief months, passing through ours. It's only the third time in recorded history that astronomers have caught something like this. The first was Oumuamua in 2017, a strange, elongated object that tumbled through our solar system so fast and so unexpectedly that by the time anyone realized what it was already too far away to study properly. Nobody had ever seen anything shaped quite like it. Some models suggested it was long and cigar-shaped. Others suggested something flatter, like a pancake tumbling end over end through the dark. It showed a small, unexplained acceleration as it left, with no visible tail, no coma, nothing that screamed comet in the way astronomers expected. That absence of an obvious explanation is exactly what opened the door, back in 2017, for wilder theories to creep into the conversation, Avi Loeb's among them. The second confirmed interstellar visitor was Borisov in 2019, which behaved much more like a conventional comet, with a visible tail and a coma of gas and dust, and which most astronomers were relatively comfortable classifying without controversy. And now 6 years later, we have 3I Atlas. The 3I simply means the third confirmed interstellar object. Its formal scientific designation is C2025N1, and that C prefix is the astronomical shorthand that tells you right away this is officially cataloged as a comet. But here's what makes this third visitor different from the first two, and why it's captured so much more scientific attention than either of its predecessors. It's brighter, it's closer, for longer, and it arrived at a moment when humanity has vastly more telescopes, spacecraft, and instruments scattered across the solar system than we did in 2017, or even 2019. Oumuamua came and went before most of the world's observatories even knew where to look. Borisov gave us a longer window but still limited resolution. 3I Atlas is the first interstellar object we've ever been able to study with this much firepower. Multiple space telescopes, multiple planetary orbiters, ground-based observatories on nearly every continent, all turn toward the same tiny point of light drifting through our neighborhood. In a very real sense, this is the first time our species has had a real opportunity to properly interrogate a visitor from another star system, and that alone is why so many scientists, on every side of the debate, consider this one of the most important astronomical events of the decade. But officially cataloged and fully understood are two very different things. Here's where the story starts to get strange. As more observatories turned their instruments toward this object through the back half of 2025, astronomers began noticing something curious about its size. Early estimates from the Hubble Space Telescope, taken in August of 2025, put the nucleus somewhere between 440 meters and 5.6 kilometers across. That's an enormous range of uncertainty. Hubble could see the coma, the fuzzy cloud of gas and dust surrounding the object, but the solid core underneath was harder to pin down. Some analyses, using non-gravitational acceleration data, suggested a nucleus closer to 500 to 700 meters. Other estimates pushed toward the multi-kilometer range. Either way, if the larger estimates hold up, 3I Atlas could be one of the biggest interstellar objects ever measured, dramatically larger than Oumuamua and significantly bigger than Borisov. Then there's the trajectory itself, and this is where things get genuinely eerie, even to scientists who aren't inclined toward exotic explanations. 3I Atlas entered the solar system on a retrograde path, meaning it's moving backward relative to the way the planets orbit the Sun, and it's inclined by only about 5 degrees from the plane in which the planets travel. Now, on the surface, that might not sound like much, but when you consider the vastness of space, and the fact that an object arriving from interstellar space could, in principle, approach from any angle at all, above the solar system, below it, sideways to it, anywhere in three-dimensional space, the odds of it happening to align so closely with the exact plane the planets travel in are startlingly low. Some calculations put the probability of that kind of alignment occurring by pure chance at around 0.2%. And it's not just the angle, it's the timing. As 3I Atlas made its way through the solar system, its path brought it remarkably close to multiple planets, one after another. It passed within about 29 million kilometers of Mars on October 3rd, 2025, close enough that a fleet of NASA and ESA spacecraft already stationed at Mars, including Mars Express, the ExoMars Trace Gas Orbiter, and several others, were able to turn their instruments and catch a glimpse of it as it flew by. Then it swung behind the Sun, reaching its closest approach to our star, what astronomers call perihelion, on October 29th, 2025, at a distance of about 1.35 astronomical units, meaning slightly farther from the Sun than Earth is. From Earth's perspective, this timing was almost inconvenient. The object was positioned on the far side of the Sun during its closest approach, making it unobservable from our planet at exactly the moment its behavior would have been most interesting to watch. Then, months later, on March 16th, 2026, it passed Jupiter, coming within roughly 53 million kilometers of the giant planet, a distance that some researchers have pointed out sits remarkably close to the edge of Jupiter's gravitational sphere of influence, known as its Hill radius. Taken individually, none of these events prove anything unusual. Objects fly past planets all the time. It's basic orbital mechanics, and with 8 major planets and countless moons scattered across a solar system this size, some degree of proximity during a multi-year transit is almost inevitable. But it's the accumulation of these coincidences, the alignment with the ecliptic plane, the close pass by Mars, the concealment behind the Sun during perihelion, the tight pass by Jupiter, that has some scientists asking uncomfortable questions. Chief among them is Avi Loeb, a theoretical physicist and astronomer at Harvard University, who has built a reputation, for better or worse, as the most prominent voice arguing that we shouldn't be so quick to assume every strange object passing through our solar system is natural. Loeb was one of the loudest voices during the Oumuamua controversy back in 2017, when he floated the idea that its unusual acceleration and shape might indicate artificial origin, possibly even a piece of alien technology. That idea was controversial then, and it remains controversial now. But with 3I Atlas, Loeb has returned to the same argument, publishing a running series of essays cataloging what he describes as anomalies in the object's behavior, accumulating by his own count into a list of more than 20 unusual characteristics that he argues deserve serious scientific scrutiny rather than dismissal. Among the anomalies he points to, the object's size, which, if it's on the larger end of the estimated range, would make it unusually massive for a naturally occurring interstellar wanderer. The trajectory alignment with the ecliptic plane, which he's calculated to be statistically improbable for a randomly arriving object. The timing of its closest solar approach, hidden from Earth's view. And perhaps most intriguingly, the non-gravitational acceleration the object exhibited, meaning its path through space wasn't just shaped by gravity alone, but showed a small, measurable extra push. Evidence, he notes, of what he describes as a remarkable system of jets. Now here's the important part, because this is where a lot of coverage of 3I Atlas tends to go off the rails. Non-gravitational acceleration isn't, by itself, evidence of anything artificial. It's actually a completely normal thing for active comets to display. When a comet gets close enough to the Sun, the ice on and beneath its surface begins to sublimate, turning directly from solid ice into gas, and that outgassing creates small jets of material blasting off the nucleus in various directions. Because the comet is rotating as this happens, those jets don't push in a perfectly uniform way. They create a subtle asymmetric thrust that very slightly alters the comet's trajectory compared to what pure gravity alone would predict. Astronomers have observed this exact phenomenon in dozens of solar system comets. It is, in fact, one of the primary pieces of evidence that 3I Atlas is behaving exactly like a comet should. And the observational data backs that up in a lot of ways. As 3I Atlas approached and then passed perihelion, telescope after telescope recorded it developing a visible coma, that hazy envelope of gas and dust that surrounds an active comet's nucleus, and a tail streaming away from the nucleus in the direction pushed by solar radiation and the solar wind, exactly the way comet tails are supposed to behave. The European Space Agency's JUICE spacecraft caught a clear image showing this tail and internal structure within the coma. Multiple observatories recorded outgassing consistent with a mix of carbon dioxide, water vapor, and other volatile compounds, the standard chemical signature of a cometary body releasing material as it warms. But even here, in the chemistry, there were surprises. In early 2026, after the object's closest pass to the Sun had triggered its most intense outgassing, the Subaru telescope in Hawaii turned its instruments toward 3I Atlas and measured the ratio of carbon dioxide to water coming from deeper inside the coma, material that had only recently been exposed by the fresh outgassing rather than the outer crust that's been baked and irradiated by billions of years of cosmic exposure. What they found was that this deeper interior ratio of carbon dioxide to water was noticeably lower than what earlier space telescope observations had suggested for the object's outer layers. In plain terms, the chemistry of this comet appears to be different on the inside than it is on the outside, and it seems to be changing as more of the interior gets exposed to sunlight. That's a genuinely interesting scientific finding, because it suggests 3I Atlas might be giving us a rare glimpse into material that has been essentially unaltered since the object's formation, sealed away from radiation for who knows how many billions of years, only now being revealed for the first time as it swings past a star. Separately, in late November and early December of 2025, two X-ray observatories, XRISM and XMM Newton, turned their instruments toward the comet and detected something that had never been seen before in an interstellar object, a diffuse glow of X-rays surrounding the nucleus. This made 3I Atlas the first interstellar comet ever observed emitting X-rays, a phenomenon that, in solar system comets, is typically produced when the solar wind, a stream of charged particles flowing out from the sun, collides with the gas escaping from the comet's surface. It's rare, it's striking, but it is, once again, a known physical process, not something that requires an exotic explanation. Then there's the water. Researchers studying the chemical signatures coming off 3I Atlas found evidence of water ice with characteristics unlike anything previously cataloged in comets from our own solar system. This detail has fueled a lot of the more sensational headlines, and it's worth sitting with for a second because it actually cuts both ways in this debate. On one hand, unusual water chemistry is exactly what you'd expect from an object that formed around a completely different star under different conditions, from a different protoplanetary disk than our own solar systems, different isotope ratios, different ice structures, different trace chemistry baked in from birth. That's not evidence of anything artificial. If anything, it's exactly the kind of alien, in the literal sense, chemistry scientists were hoping to find when they first realized an interstellar object was heading our way. It's a genuine scientific treasure. A sample, however indirect, of material from another star system delivered to our doorstep for free. On the other hand, it's precisely this kind of "we've never seen this before" language that gets pulled out of scientific papers, stripped of context, and repackaged into far more sensational claims online. And that's the tension running underneath this entire story. Almost everything unusual about 3I Atlas has a plausible, well-understood natural explanation rooted in comet physics, and in the simple fact that this is our first really detailed look at a genuinely ancient object built somewhere else entirely. And yet, when you stack enough of those unusual details on top of each other, the size, the trajectory alignment, the timing near planets, the unprecedented X-ray emission, the anomalous water chemistry, the non-gravitational push from its jets, some scientists argue that the cumulative improbability is worth taking seriously, even if no single data point proves anything on its own. This is really the crux of the disagreement, and it's worth being honest about where the broader scientific community stands. The overwhelming consensus among astronomers actively studying 3I Atlas, including the teams behind NASA's Hubble, Webb, and TESS observations, the European Space Agency's Mars and JUICE missions, and independent research groups using the Subaru telescope, is that this is a comet. A genuinely remarkable one. Quite possibly one of the oldest, most pristine objects ever studied by human instruments, a frozen time capsule that formed around another star before our own sun had even ignited. But a comet, following the well-understood physics of outgassing, solar heating, and gravitational trajectory nonetheless. Avi Loeb and a smaller group of researchers argue that the scientific community may be too quick to default to the conventional explanation, and that given how rare interstellar visitors are, we've only confirmed 3 in all of human history, every single one deserves to be scrutinized against every possible hypothesis, including the uncomfortable one, that it might not be natural at all. Loeb has been careful, in his own writing, to frame this less as a firm claim and more as a hypothesis that should be tested rather than dismissed outright, pointing out that history is full of moments where the boring explanation was assumed too early, and the more interesting truth only emerged because someone kept asking questions. It's worth understanding a bit more about how Loeb builds his case, because it's not built on a single smoking gun. It's built cumulatively, essay by essay, data point by data point, published openly as new observations roll in from observatories around the world. Each new piece of data, whether it's a fresh Hubble image, a new spectroscopy reading from Webb, or an updated orbital calculation from JPL's tracking systems, gets folded into his running tally of anomalies, and he's been transparent that many of these, taken individually, have mundane explanations. His argument isn't that any single data point proves artificiality. It's that the sheer number of them, and the specific combination of them, a size on the upper end of what's typically observed for interstellar objects, an alignment with the ecliptic that would be statistically rare for a randomly tumbling object, a trajectory that conveniently hides its closest solar approach from Earth's view, and non-gravitational acceleration patterns that don't perfectly match the outgassing profile of a typical icy comet, is enough, in his view, to justify the hypothesis being tested rather than dismissed. He has repeatedly framed this as good scientific practice, arguing that the same rigor applied to searching for exoplanets, gravitational waves, or dark matter should be applied here too, rather than assuming the mundane explanation by default, simply because it's the more comfortable one. Critics of that position, and there are many, including senior astronomers at NASA and other institutions, argue that this approach inverts the basic principle of scientific reasoning. Extraordinary claims require extraordinary evidence, and right now, essentially all of the observed behavior of 3I Atlas falls within the known, if wide, range of what active comets can do. The improbability of its trajectory alignment, they'd argue, isn't the same as impossibility, and improbable things happen constantly across a solar system that has existed for 4.5 billion years, hosting countless flybys, alignments, and gravitational near misses that nobody was around to record. Statistically unlikely is not the same as artificially engineered, and an object behaving exactly the way physics predicts a comet should behave, developing a coma, growing a tail, outgassing volatile ices, showing measurable but modest non-gravitational acceleration, is, they'd say, doing exactly what you'd expect a comet to do, not what you'd expect a spacecraft to do. It's also worth noting that NASA has made an enormous amount of the raw observational data on 3I Atlas publicly available, specifically so that independent researchers, students, and citizen scientists around the world can dig through it themselves rather than relying solely on official interpretations. More than a dozen NASA missions turned their instruments toward this object over the course of its passage. Hubble, Webb, TESS, Sphere-X, the Psyche spacecraft, the Stereo mission, even the Lucy spacecraft, which was on its way to study the Trojan asteroids near Jupiter and happened to catch a distant glimpse of 3I Atlas from nearly 240 million miles away. That kind of coordinated multi-instrument observation campaign is unprecedented for an interstellar object, and it exists precisely because scientists recognized how rare and valuable this particular visitor was, regardless of which side of the natural versus artificial debate they land on. The James Webb Space Telescope's contribution deserves special mention here, because its instruments are built specifically to detect the kind of faint chemical fingerprints that other telescopes simply can't resolve. Using its near-infrared spectrograph, Webb was able to break down the light coming from 3I Atlas into its component wavelengths, effectively reading the chemical barcode of the gases boiling off its surface. Later, on a follow-up pass, Webb's mid-infrared instruments captured what researchers described as the first detailed thermal chemical fingerprint ever collected from an interstellar object, offering clues about the ancient environment in which this comet originally formed, potentially billions of years before our own sun ignited. That's a staggering thing to sit with. The material streaming off 3I Atlas may have been locked in ice since before Earth existed, since before the sun existed, drifting through interstellar space for untold eons before finally being warmed by starlight again, for the first time in its existence, right as our own telescopes happened to be watching. Meanwhile, back on the ground, observatories large and small joined the effort. Amateur astronomers with modest telescopes captured their own images of the fading object as it receded past Jupiter, contributing data points to a growing public archive that professional researchers have used to refine trajectory models. This kind of open, global collaboration is relatively rare in astronomy, and it's a direct result of how much attention 3i Atlas generated the moment its interstellar origin was confirmed. Everyone, it seemed, wanted a piece of this story. Professional astrophysicists chasing publishable data, amateur skywatchers hoping to catch a fading dot before it vanished for good, and millions of ordinary people online watching the debate over its true nature play out in near real time. So where does that leave us? As of now, 3i Atlas has already made its closest approach to the Sun, already swept past Mars and past Jupiter, and it is now well on its way back out of the solar system, fading as it goes. Recent imaging places it more than 1 billion kilometers from Earth, nearly 7 times the distance between the Earth and the Sun, and it's continuing to recede, moving in a path that mirrors, almost symmetrically, the way it arrived. It came from interstellar space, it briefly crossed through our cosmic backyard, and now it is leaving permanently, never to return. Whatever this object is, we are watching it disappear back into the dark it came from. And this may be the last real chance humanity has to study it up close for a very long time, possibly forever, unless we manage to catch another interstellar visitor someday on a trajectory close enough for our telescopes and spacecraft to reach. And maybe that's the part of this story that deserves more attention than the alien question. Whether 3i Atlas turns out to be nothing more exotic than an extraordinarily old, extraordinarily well-preserved comet, or whether, decades from now, some of Loeb's more provocative hypotheses end up looking prophetic rather than premature, the honest truth is that either outcome is remarkable. If it's just a comet, it's a comet unlike any we've ever studied, a piece of another star system, chemically distinct, structurally ancient, offering scientists a genuine window into the conditions that existed light years away long before Earth ever formed. If it's something else, then we've just watched in real time an object pass through our solar system that would rewrite everything we think we understand about our place in the universe. The truth is, we may never fully resolve this argument. 3i Atlas is already too far away and moving too fast for us to send anything to intercept it, to land on it, to sample it directly the way we have with asteroids and comets that actually belong to our own solar system. Everything we know and everything we'll ever know about this object comes from the handful of months in late 2025 and early 2026 when it happened to be close enough and bright enough for our telescopes to catch a glimpse of it as it passed. Every photon of light, every spectral line, every X-ray photon that these observatories managed to capture is now the entire dataset humanity has and will ever have on this particular visitor. So is 3i Atlas an asteroid? Technically, of course, no, it's officially cataloged as a comet. Or is it something far more advanced, a piece of engineered technology cloaked in the appearance of an icy relic, deliberately or coincidentally, threading its way past 3 planets on its way through our solar system? The mainstream scientific answer, backed by the overwhelming majority of data collected across a dozen missions and multiple independent observatories, is that it's a comet, an old one, a strange one, a scientifically priceless one, but a comet nonetheless, behaving according to physics we've understood for centuries. The minority position, championed most vocally by Avi Loeb, is that the accumulated improbabilities are enough to keep the door open, even if just a crack to a stranger possibility. It's tempting, in stories like this, to want a clean resolution. We want the scientists to hold a press conference and declare, definitively, one way or the other, exactly what this thing was. But that's not how frontier science actually works. And it's certainly not how it works when the subject in question is already halfway back to interstellar space by the time the most interesting data starts coming in. Real scientific consensus builds slowly through years of peer review, competing analyses, and repeated attempts to poke holes in every hypothesis until only the strongest explanation survives. For 3i Atlas, that process is still ongoing, and it will likely continue for years, long after the object itself has faded from view. Papers are still being written. Data is still being cross-checked. Independent teams around the world are still rerunning the same non-gravitational acceleration models, trying to see whether Loeb's calculations hold up under scrutiny, or whether they collapse once measurement uncertainties are properly accounted for. What makes this particular case so compelling, though, isn't really about whether Loeb turns out to be right. It's about what this entire episode reveals regarding how we, as a species, respond to genuine uncertainty. For a few months in late 2025 and early 2026, a huge portion of the world's astronomical infrastructure was quietly, cooperatively focused on a single, fading point of light, trying to answer one of the oldest questions we've ever asked. Are we alone? And in the process of trying to answer that question responsibly, scientists ended up doing something remarkable almost by accident. They produced one of the most detailed, most thoroughly cross-referenced data sets ever assembled on an interstellar object, one that will be studied and restudied for decades, regardless of what final conclusion the mainstream consensus eventually settles on. There's also something worth sitting with in the sheer scale of what was accomplished here, technically. 100 years ago, we didn't have the tools to detect an object like this at all. 50 years ago, we might have caught a brief glimpse with no way to analyze its chemistry or trajectory in any meaningful detail. Even a decade ago, our ability to coordinate observations across ground-based telescopes, orbiting space telescopes, and planetary spacecraft scattered across the solar system was nowhere near what it is today. The fact that we caught 3I Atlas at all, tracked it continuously for the better part of a year, measured its chemistry down to isotope ratios, imaged its structure with multiple instruments, and detected X-rays coming off its coma for the first time in the history of interstellar object research, is itself an extraordinary technical achievement independent of whatever this object ultimately turns out to be. The truth is, we may never fully resolve this argument. 3I Atlas is already too far away and moving too fast for us to send anything to intercept it, to land on it, to sample it directly the way we have with asteroids and comets that actually belong to our own solar system. Every future spacecraft mission concept that's been floated to chase down an interstellar object like this one would require years of advanced planning and a launch vehicle already waiting on a pad the moment a new candidate is discovered, technology and infrastructure that, as of today, simply doesn't exist yet. Everything we know, and everything we'll ever know about this particular object, comes from the handful of months in late 2025 and early 2026 when it happened to be close enough and bright enough for our telescopes to catch a glimpse of it as it passed. Every photon of light, every spectral line, every X-ray photon that these observatories managed to capture is now the entire dataset humanity has and will ever have on this particular visitor. What nobody disputes is this. For a few short months, something from outside our solar system formed around a star we will never see, shaped by forces and conditions we can only guess at, passed silently through our cosmic neighborhood. Close enough for us to watch, to measure, to argue about, and then it kept going, back out into the dark, carrying its secrets with it, leaving us with nothing but data, questions, and the uneasy, thrilling reminder that we are not alone in an empty solar system. There are visitors passing through on their way from somewhere to somewhere else, and every few years, if we're lucky and if our telescopes are pointed the right way, we get to catch a glimpse of one before it disappears again for good. Whether 3I Atlas was just a comet or something we don't yet have the words for, one thing is certain. It came from another distant star. It quietly passed through our home. Now it's gone. Somewhere out there, another one is already on its way, drifting toward us right now, unseen, unnamed, waiting for the next telescope, the next lucky night, the next set of curious eyes to look up at exactly the right moment and ask the same question all over again.